Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 11th, 2026, about 6 days ago. It introduces an open-source mobile manipulator that aims to solve the hardware accessibility crisis in robotics by delivering a capable bimanual system for a bill of materials, cost of approximately $9,250. The paper is titled YOR, Your Own Mobile Manipulator for Generalizable Robotics. And, as we'll see later, the system demonstrates some really impressive capabilities in autonomous navigation and manipulation tasks, despite the low budget. To visualize the hardware, Figure 1 details the system's modular design, which centers on keeping costs low without sacrificing capability. At the bottom, you see the omnidirectional base housing a 24-volt battery and a Raspberry Pi 5 for low-level control. Rising from this base is a telescopic vertical lift that adjusts the shoulder height between 48 and 124 centimeters. To handle manipulation, the top section mounts two 6-degree of freedom arms with custom grippers and a Z2i stereo camera, all processed by an onboard Jetson AGX Orin. So, Figure 2 places this design in context by comparing YOR against other popular mobile manipulators like TidyBot++, XLE Robot, and Mobile Aloha. The highlighted column shows that YOR occupies a unique sweet spot. It is the only platform in this price range that combines bimanual manipulation, an omnidirectional base, and vertical control. While the XLE Robot is significantly cheaper, it lacks payload capacity, and robust systems like Mobile Aloha or the commercial RBY-1A cost 3 to 8 times as much, without necessarily matching YOR's vertical reach or agility. Alright, Figure 3 breaks down that $9,250 price tag component by component. As the chart shows, the bulk of the budget goes into the two arms, costing $5,100 combined, followed by the mobile base at $3,000. Interestingly, the vertical lift is extremely cost-effective at just $200, which is key to keeping the total bill low. The diagram also separates out an optional $1,500 cost for simultaneous localization and mapping, which covers the high-end Jetson Orin and Z camera needed for advanced autonomy. Well, having covered the hardware costs, Figure 6 demonstrates the robot's actual performance on a complex recycling task. Here, the system uses an imitation learning policy trained on about 100 demonstrations to autonomously coordinate its base and arms. In the sequence, the robot grasps a box with both hands and lifts it using the telescopic spine. It then navigates around a wooden obstacle without dropping the payload, effectively combining locomotion and manipulation. Finally, it approaches the blue bin and deposits the item, proving that the low-cost design handles robust, whole-body tasks. Okay, having shown the robot can handle objects, Figure 10 tests exactly how precise its navigation is over time. In Panel A, the robot drives a loop through the room and attempts to mark the exact same spot on a sheet of paper each time it returns. Panel B visualizes this trajectory inside the robot's simultaneous localization and mapping system. The result in Panel C is striking. After 10 loops, the ink marks cluster tightly within a 12mm radius next to a US nickel. This proves that despite the budget components, the odometry is accurate enough for reliable tasks. So, while the hardware provides the body, this table details the brain, listing the hyperparameters for the versus qubit policy. The system uses an observation context of 3 frames and an action chunk length of 10, which allows it to plan smooth trajectories. The network itself is quite compact, with an embedding dimension of 512 and a depth of 6 layers. Training is handled by the Atom W optimizer, using a batch size of 512 and a learning rate of 6 × 10⁻⁴. Alright, for those looking to actually build this, Table 1 provides the granular bill of materials that sums up to that $9,200 figure. You can see the heavy hitters are the 2 Piper arms at $5,000 combined and the Max Swerve modules for the base at $2,700. The list is incredibly detailed, breaking down everything from the Raspberry Pi 5 compute module to the specific aluminum extrusions and even the nuts and bolts. This level of transparency really reinforces the project's goal of being a reproducible, open-source platform for the community. Wrapping up, the main takeaway is that YOR proves capable mobile manipulation does not require a 6-figure budget. By open sourcing a modular design under $10,000, this project effectively democratizes access to real-world hardware, allowing more researchers to test ideas physically rather than just in simulation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.